This is Physics Lab 5, Magnetic Braking with Faraday by Camille Branch. And the table of contents is here. So for the introduction, the purpose of this lab is to study magnetic induction, and eddy currents by analyzing observational data of a bar magnet falling through a tube of aluminum foil and comparing it with the computational model using GlowScript. The system is the bar magnet, an aluminum tube, and the surrounding is the Earth. And then for a preview of results, we have our average experimental time is 1.8 seconds, and the average computational time is 1.018 seconds. Fundamental concepts. So some of the fundamental concepts in this experiment will be Newton's second and third law, where one says the net force equal to a change in momentum over time, and then Newton's third law says for every action there is an equal and opposite reaction. New concepts are Faraday's law, which means that EMF, or the electromotive force, is equal to negative number of turns, or N, times delta flux over delta time, which is just a voltage. And then we have the Biot-Savart law, which is the magnetic field is equal to the K constant, which is mu naught over 4 pi. Times the current times the length of the tube crossed with the unit direction, all that over r squared. Okay, so for the procedure, okay, and so what happened was we just take an aluminum tube, we take the measurements of its length, its width, and its inner width, like the inner radius, and then we measure how long it takes for the magnet to fall to the bottom. And we got that, and for 5 trials we got that it took an average time of 1.8 seconds. Okay. In GlowScript, we have the initial conditions and physical constants there. And then to calculate the magnetic field, you basically are using the B equals, so it's the K constant times 1 over the magnitude of R cubed, and then you're multiplying that by each direction of the mu, the sum of that. And then you just calculate the magnetic flux by doing a flux over time thing. Okay, and then you're gonna find the gravitational force of the bar magnet, as it travels down the tube. And that is just your mass times the gravitational acceleration. And then the current is just the flux, the change of flux over the ring. And then basically you're gonna compute the magnetic field of one ring, and that will apply to all the rings. And that's kind of the same thing we did before. And then to find the net force, you just add the gravitational force and the magnetic force. The first section of the graph after the code has ran is the gravitational force greater than the magnetic force. The second part is terminal velocity, and the third part is the gravitational force less than the magnetic force, and that's wrong. And in the code, the time to complete is 1.018. And then some errors that could have happened during the experiment. We had an old magnet, air resistance was considered, and then the stopwatch measurement could have been more accurate. And for the what if questions, answer the first one. If you decrease the resistance, you increase the current, which makes a stronger induced magnetic field, and slows down the magnet. And for the second question, If you have less current rings, which means you have like holes or slots into the tube, it equals a weaker induced magnetic field, and that will cause the magnet to fall faster. Thank you for watching.